that look so slow?
Nice. Build. Hide. There you go. Jump.
I think it looks like 3, 3, 1. That's scary. You like killed 10 dudes with them.
Build. Build. Okay, Maverick clutched it.
Welcome everybody. Welcome my young apprentices. How is everybody in the chat? Can everybody hear me, and how laggy is it? Is it better than before? This here. Better so far. Okay, that's good. And as you can see, here you got chat is now on the video. So that's part of the video. So that way when you're looking at it on YouTube, you can still see it now. So yes, be aware for that. That is now for the YouTube, because on Twitch you can see the chat, but then otherwise we couldn't see the questions. So now it's a little bit clearer for people that are watching on YouTube when there's a question. I try to say the question beforehand, but that's not always the case because I forget. So yes. All right then, let's go ahead and jump right in. Okay, so that's going to be a problem, that we have white chat on white background. So yes, that will be something that I'll have to fix. It's there, it's just not visible, see? So, okay, so don't worry, I will take care of that for the next time. I didn't think about that, but yes, indeed. I mean, I could just leave it like that for now, but we don't need to see that one. But you know, okay, it's all good. At least you can see your names, and then if there's a question, I suppose I'll try to do that. But okay, all right. So today you know, until the end of the semester, we'll most likely have the class at the same time. So there's your times. And today we're going to be very briefly reviewing about breadth first search. And then now we're going to jump into depth first search, topological sort. I'll spend a little bit of time on depth first search, just like I did with breadth first search in terms of the algorithm itself, after explaining to you the overview. And then hopefully we get into minimum spanning trees, and I can show you at least the introduction of that, the overview, and then we can talk about the actual in-depth algorithms. You'll learn 2 of them on Thursday, and then hopefully we will be done with the minimum spanning trees on Thursday, because you have an assignment that requires the minimum spanning trees. I am using Streamlabs chat, so you can add an outline for the change of colors. You know, I might be able to do that really, really fast. So let me give that a shot. Do you know where the setting for that would be? Let's just try. Let me log in. Okay. So I am here now in Streamlabs. So I'm chat. All widgets, chat box. So yeah, so the next assignment 11 has to do with minimum spanning trees, but it has to do with just more than that. It is, you have to make a graph, and then after you're done with the graph, then you perform minimum spanning tree on that graph. So you can get started already on doing everything but the minimum spanning tree. You can make the graph, you can make everything, and then just leave the spot for the minimum spanning tree, which you can then add on after Thursday's class. So I am now in Streamlabs here. Where would I add that background? Background color, text color. It will not show in your streaming software. I don't think there's an easy way that I can do that, but I can try to change the text color. So let's go ahead and do red. And then, did it work? Yeah, there you go. It worked. So I think we'll stick with red for now, just because that seems to be less likely to happen between the different change of colors. So yeah, we'll go with that for now. And then I will experiment on different combinations later, but at least for now, you can see chat. And I was thinking of pretending to emulate Valorant so that you could have Valorant drops while we were watching this, but that was too much effort. Plus, I don't want random people to come in thinking this is actually a Valorant stream and get confused and then troll the chat. Yes. I also switched it to follower only mode for the chat. That way I can moderate it. Not mostly for you guys, but for the afternoon class. Plus, I get the added benefit, I guess, it's temporarily getting more followers. I don't know. So, anyways. So, okay. Cool. So let's go ahead and then get started on this. I do want to say that I did make a big announcement about 2 days ago on the email. You should have gotten that about a bunch of things. I don't think that I have anything to clarify on that other than, like I said, there is an assignment 11 that you should get started on. There is an extra credit portion to that assignment, I believe. If you want to do it, it's optional. Your tests will be graded eventually, and you should be able to see the tests themselves now if you log into Canvas, like as in like the test questions. And then once you get your grade, you will get 1 grade, but then if you click in there, you can see the breakdown by points of each question. So as for going over the test itself, I was thinking of doing a separate stream for the test review, like not review, but I guess like post-mortem. I don't know how would you call it. If I do that, I'll do that on like a Friday or Saturday, and then I'll stream it, and then I'll record it it'll be recorded on Twitch, and then you can watch it on your own time, and that will help you, I guess, a little bit in preparation for the final, but also so that you can see whether or not you were graded correctly as well, in case there's any sort of issues. So post-mortem also doesn't just mean after that. Post-mortem also means after the fact. So yes, there's a use of post-mortem that does not just include people dying. Don't worry. Google this. Okay. Yeah, so the average was 2 hours and 52 minutes. That's right. Although section 1, that's the 9:30 a.m. class, won in terms of speed because they were like at 9:48 or something like that. So I'm proud of them for that. Well done, 9:30 a.m. class. Okay, so all right, I think we're good on everything. So actually, I'm going to back out of this tab and go into the one from last class just to review breadth first search. And I think that's actually on the top. So we did a lot of review that day. Yeah, okay. So we had a graph, right? And we have when you're doing breadth first search, that's your traversal, so that's like your level order traversal, but in the graph. That's kind of like if you were grabbing the node. Has the mic been pulled close? I have pulled it close. I can pull it a little bit closer. I can even go like this if you'd like. But yeah, so it's like grabbing the node where you're starting from. I'm pulling it so it becomes like the top, kind of like if it was a tree. And then if the thing was hanging down like that, then it would be each level, just like it was doing when you were doing trees for the breadth first search. So yes, okay. So you know, in our case here, S is a starting node, and so in the breadth first search traversal, we want to print out all the nodes that are connected directly to the root first, so to have the edge connecting them. So in this case, ACG, and then the next sort of layer are the ones that are 2 edges away from the root. So you have to visit a vertex one, and then go to the vertex, the second vertex, the one that you're printing, and so that actually applies to all of these. So B, D, E, F, and H are all two hops per se from the root. And so, you know, when we printed a traversal in level order, we went from left to right. But it doesn't really matter if we go left to right, because there is in the graph, there's no top, bottom, left, or right. It's like space. There's no north, east, west, south, and space. It's just space. There has to be a sort of a relative point that you base it off of. So in this case here, it doesn't really matter whether like A, B, if you got A, C, and G, which are directly connected to C, or sorry, to S, it doesn't matter if you put C first or A. We just like to go with the alphabetical stuff because when we do program it, we have to decide between 2 things that are the same. We got to pick one. When we're doing the trees, we just said go from left to right. From here, because it's not as easy as left to right, we're just saying just go alphabetically. So yeah. Ultimately, though, there is more than one way to draw a graph, but it represents the same graph. So it's just as easy as saying, suppose that I took the B, the arrow of the B that's like this. So you got A to B, and I just twisted it somewhere like that. Then, you know, that's still the same graph. It looks different, but it's the same graph, right? In fact, there's a very, very hard problem with graphing, and by problem I don't mean like actual problem, I mean like mathematical sort of challenge, that try to draw a graph where no 2 edges cross each other. Like you're trying to draw a graph like this graph right here, you see I'm not crossing any lines, right? It turns out that the more vertices you have and the more edges you have, the harder it is to achieve that, and sometimes it's actually impossible. So for example, if this graph was connected with everything else, it would be essentially impossible to do it. And there's a math formula that says that, when it's actually impossible. But you know, yeah, it's kind of like the Euler bridges and Hamiltonian paths kind of thing. So we got a lot of discussion in the chat. So let's see. Just your question can be the general would have been rotated. The ABL trees. So yeah, so that's the one thing. So with the tree, you know, left and right matter. You know, it's very, very important for binary search tree at least. Here, there's no such thing as left and right, up or down. There's nothing. It's just a child. You know, when we look at A and it has 2 children, we have to per se, you know, B and S. First of all, because this one's a undirected graph, unordered graph, there's no direction, right? So it's not like a tree where like you have a parent and a child. Here, it's like they're both each other's parent and they're both each other's child. Like it's just a connection. And so again, it doesn't matter if I flipped the entire graph and A was like the axis that I flipped it on, it wouldn't matter. So there is no such thing as a as a balanced graph per se in reality, as you would consider with a tree. You know, because I mean, if you were looking at the breadth first traversal of the graph, and then you said, okay, I want all the nodes to be as close to the root as possible, then you could just connect them directly. You could just make them all directly connected. You make a strongly connected graph in the case of a directed one, or just a graph where there's an edge coming from the starting node to the ending node instead of just a path. You know, so and that would be, one time I suppose, but it's not really. So it's kind of, I don't want you to think, I want you to transcend the trees and now move up to graphs. Don't try to think of those algorithms as applying necessarily to graphs. It works the other way around. The bigger set is graphs, and then a subset of that, really tiny, is going to be your trees. And within that subset, really tiny, there's binary search trees, right? And then within that tiny little subset of just trees as well, there's linked lists technically, which are your degenerate trees or anime trees, right? So ultimately, these algorithms are only applying for certain subsets here. They don't necessarily extend to the entire thing. So would each node have 2 pointers? Each node would have potentially, okay, so we talked about representing a graph with adjacency list and adjacency matrix, but if you were to implement it using just pointers, then what it would be an array of pointers that you would dynamically allocate based on the degree of the graph, the out degree of the graph. The out degree of the graph, I think I put it here, is the number of edges that are leaving from a vertex V. So that means how many, per se, children there are. So for example, the out degree of vertex S is 3, whereas the out degree of vertex C is 4. Now, because this is an undirected graph, the out degree and the in degree for the same vertex are going to be the same. So like there's 3 edges coming into S and there's 3 coming out. If it was a directed graph and say that A to S was coming into S and then S to C and S to G were coming out, then we would say the out degree is 2 and the in degree is 1. Why did that come up? I don't know, something on the chat made me talk about that. Oh, because of the implementation with pointers. And so with pointers now, you don't care about the in degree because that's someone pointing to you. Just like in a linked list, you don't care who's pointing to you. It's more of you want to point somewhere out, you need to create those pointers, but you can't just give them constant names like left, right, top, down. You can't do that because you run out of names really fast. And some of them may or may not have that many out degree levels. So because of that, you just make an array and you dynamically allocate the array. So you just set up a quote unquote double, 2 asterisk pointer, which is going to point to an array of pointers, which you just dynamically allocate as required and keep a size. Or you can use a vector as well and not worry about that. But the point is you keep all the pointers nicely kept in a little loop that you can run through and work with them as necessary. And you'll get to experiment some of this, maybe not in assignment 11, because in that one I gave you the option to use adjacency list matrix instead of just doing pointers. But I think in 12 we will actually try out the pointer approach, and so you'll get to experiment implementing that. Or if you do the extra credit with the tries, you also need to have an array of pointers based that is dependent on that one. Is more like there's a limit to the size because there's a limit on the character count. But if there wasn't, then you could also apply the same logic. Can you go over the breadth first search example with a queue again? Yes, that's just literally what I'm about to do right now. So would each node, okay, let's run that. So, all right, cool. So I think I'm up to date. And then I gotta keep an eye on that. I have another class. Oh, yeah. So yeah, don't forget, if you can't make class, I will upload the lecture to YouTube, unless I forget to record, which I didn't today. That one day that I forgot, though, I was able to pull it from Twitch, which I'm glad it wasn't the day that the Twitch thing broke and it said I was streaming for like 36 hours, which that's just an act, a divine act there, because I did accidentally leak one question from the test and the whole thing broke down. And so I when I try to go and see like, oh, maybe I should try and see if I can censor the question out, I couldn't even access it. And I was like, well, I guess I'll access it later. And then at some point it said I stopped streaming after about 38 hours, 36 hours. So, okay. So the breadth first search, I already talked about what it is. So I'm just going to talk about how we deal with the queue, right? And that's okay because you'll see that the algorithm for depth first search turns out to be the exact same, except instead of using a queue, you use a stack. And that's pretty much the only difference. However, there is another way of doing depth first search. Anything that has a stack in its algorithm can typically be done also using recursion, because then you can use the call stack as your stack. And that's pretty much what we did in 202 if you took it with me on the inception assignment. So yes, we didn't have to actually code a stack by hand. We took advantage of recursion and the fact that it works in sort of the same manner. So, okay, so we got our graph here. And again, S is our starting point. And the way that it works is you have an empty queue at the beginning. You have what's known as a array that marks whether a node has been visited or not already. And then you have your output, which is your traversal as things come out. And the one thing that we want to make sure that you don't forget, and that I almost screwed up, is that when you start with your node S, you add it to your output because that's always going to be the first thing. Your root's always your first thing per se. Same thing with the tree. And then any node that's connected to it, so there's a direct edge, so in this case A, C, and G, are going to be thrown into the queue. It doesn't matter, again, which one you put in first, because when you have to code this, you have to pick, so you can just go alphabetically, or however it's stored in memory in your implementation. So you put A, C, and G in the queue. Then you mark S as visited, because you already were there, but you do not mark A, C, and G as visited. And you're only adding things to the queue that have not been visited yet, which in this case is everything. Okay, so, and I guess I don't want to, well, yeah, why not? Screw it. So we'll draw in here. It'll update the PDF. Okay, and so now the next step is going to be to pop whatever is next left on the queue. Or I suppose instead of pop, because pop is more of a stack term, it's dequeue. So when the amount of leaf nodes are arbitrary, what's the best way to store pointers? A vector, an array of pointers, or a vector? Anything that's just dynamic, because that way, the only thing you're keeping in your class is just going to be a pointer to the data structure that contains all of the other pointers. And then that data structure implementation is up to you. It can be a dynamic array, which is very popular. You could even do a linked list if you wanted. You could do a vector. Anything that is dynamically sizable, as you said as well yourself. So yes. Okay, so then we got A, C, and G. So what we're going to do is we're going to just pop out the, or dequeue the next letter on the front of the queue. So that's A. And then you mark A as visited on the visited array. So then you would put it as a 1. And then from there, you look at everything that A is connected to, which in this case is B and S. You're going to add B because you've never visited, but you're not going to add S because it has already been visited and it was marked as visited as such. You can see it right there. We already marked that. Well, we marked everything, but we would have marked S at the beginning of this one. We did it. And so after you add just B and not S, then you can go ahead and say you're done with A, and then B gets added here, and then you just rinse and repeat that. So I'm going to kind of speed that up there because you can always just watch the video again as well, But ultimately, that's what you do. You keep adding things to the queue, and then you take it out. You put to the queue anything that's connected to that's not been visited yet, which in this case, when you get to B and you're actually working on B, you would not add A back because you already visited. And that's pretty much it. So I'm actually going to go ahead and steal the same graph here, and we'll use that for our depth first search algorithm. So let's go ahead and do that. Okay. Okay, so let's talk about depth first search. And by the way, just remember, with depth first search, there's more than one answer just because of the ordering of the vertex, right? Vertices. Same way with depth first search. There's going to be more than one answer. In fact, there's probably more answers in depth first search than there is for breadth first search, probably. Don't quote me on that, but it just feels like that, at least when you do it. So how does depth first search work? Okay. Hopefully this is a little bit of review from 202, but if not, don't worry. So the way depth first search works is like a very greedy algorithm. And by greedy, and we'll talk about the last week on different types of algorithms after, and then we'll wrap the semester by doing that, talking about each of the algorithms we discussed and which class they fit on and so on. So we'll come back to what greedy really means. But for now, I want you to think of it as follows. When you're trying to solve a problem, instead of having some sort of big meta of how to approach it, you're just going to try to solve one piece of it. And then if you solve that piece, then you're going to try to solve the next step. And you're going to keep trying to get closer to the end of the goal until you hit a wall. And if you hit a wall, then you'll back out and try another approach. And then if you hit a wall there, then you'll back out and hit another approach. So what would that look like visually? Okay, well, suppose that you have, you start out here and you're trying to solve a problem and there's 3 choices. You have to take a choice. So you take this choice as one of the solutions to your problem that you're going to approach. And that actually brings you to another choice, maybe that. And from there, you take this choice, the middle one. And it turns out that from there, you get to the end of, or maybe you go one more, but this here, you only have one choice. So you just take that one choice. You have no other choice. You get here. And then at that point, maybe you hit a wall and you're saying that is not the solution to your problem. So what do? Well, you try other choices. But instead of just going back to the root, what you do is you back out one step at a time. You back out here, but since you only have one choice, that doesn't get you much. So you back out here, and now you have 2 more choices you can go. So maybe you try this way, and you get here, and here there's 2 choices. And you try maybe this one. It doesn't matter which one you pick, you just pick one. You get here, that's not the solution to your problem, so you back out, and now you try this one. It's not a solution either, so then you back out, you're here, there's no more choices, you back out again, and now you try over here. And maybe this is the solution to your problem. That's it. That's the solution to your problem. Okay, that's good. Could there have been an algorithm that would have achieved it faster and better? Possibly, but it's not as easy as you think, because as you saw, I was drawing the tree, or in this case graph actually, I was drawing the graph as I sort of went into the graph. And that's because I can't see what's beyond my current sort of decision. So like, it's kind of like you're driving and you're lost and you're hopefully trying to get out of wherever you are, and you hit a crossroad, and there's no signs. You don't know where each of those will take you. You just hope that you go one way, and then when you get to the next crossroad, you can see it. Unless that crossroad was like where you're visually away, but you can see each of these like 100 miles away, you have no idea what's going to be ahead of you. And so that's the same way with a traversal. You don't know what's ahead of you until you get to that crossroad. And if you find that that's not the way to go, and you only have one way to go back, to go is going back. So you go back to the last crossroad and you try a different crossroad and hope for the best. There's no really an efficiency in all the way from here, driving all the way back here, and then trying an entire different path. No. It's much easier to just try the next closest available thing. It's like you're being lazy or conserving as much fuel as possible. So if you go back here, if you go from here and you go back here, you're going to try this approach here because you haven't tried it yet, and it's the one that would take the least amount of fuel. So yes, in a way, you're just making arbitrary choices and hoping that it works out. That's a good way to put it. And so that's basically how depth first search works. And it's another way of doing traversals. So just like breadth first and for a graph. And we've actually technically kind of done depth first search when we were talking about trees, because we had pre-order, in order, and post order. And which of those, chat, do you think most closely resembles what I'm talking about here with depth first search? So I'm looking at you. Come on. Post order. There we go. Not level order, not in order, but I'm glad that the first person that posted it got it right. And that is indeed post order is the closest one, because that's very greedy. The way post order works is you either go left, you go right if you can, and then if you have no choice, so it means you cannot go further left or right, that's when you go ahead and you print your node. And so, but the only way you can print it is if you have no more children to go, which means you're a leaf node. That's when you hit that wall. That's going to be the closest thing to post order. However, there could be an argument made that the other two traversals could potentially be a form of depth first search. Because if you're doing, for example, pre-order, right? Pre-order is to print and then go left and then go right. That's still greedy in a sense that, yes, you're printing as you're arriving. So it's like you're keeping track of where you've been, but you're still trying to go as deep as possible, right? So I would say that that's also a valid pre-order, you know, although post-order is the most sort of quote unquote obvious. What about in order then? Because some people said in order, you know, and, you know, there is an argument to be made that even an in order traversal is also a depth first search. Again, you're just simply saying that if you get to a crossroad, you're always going to go left because you lucky left or something. And so essentially, that's basically saying go left as far as you can. And when you cannot go left any further, then go ahead and print out where you've been and then try to go back. And then at that point, because you came back and you went left, now you're going to go right. So I'd say that all three of them actually, it's a little bit of a trick question, would be a depth first search. Although most people like to think of post-order, as an initial sort of example of depth first search traversal. So let's go ahead and perform, without doing it algorithmically, just conceptually for now, a depth first search traversal on this graph. So the first thing that you should ask me now is, where do we start? Because depending on where you start, it's going to matter. With trees, you always start on the root, but there's no such thing as a root on the graph, right? Well, yes, there isn't technically, but usually you have a starting node and you consider that your root. And in this case, we're going to pick the same one that we did for the breadth first search, which is your S. We're going to pick S to be your starting node. And so let's go ahead and before I ruin this beautiful picture of a tree, or sorry, graph, let's make a backup of it. There. Okay. All right. So let's pick a color, maybe green, and let's go ahead and perform our depth first search. So we're going to start out at S, and then we have three choices of where we can go: A, C, or G. It does not matter where you go, but we're going to try alphabetically as a decision maker. But again, it doesn't matter. Okay. In fact, actually, let's not do alphabetical. Let's just kind of go with it. Go with the flow. Okay, so we started at S, and so we're gonna go to C. And from C we got three choices, and so we're gonna go to D. From D, we hit the wall. We hit the leaf. Right? There's nowhere else to go. So that's when you backtrack yourself. So I'm not introducing the concept of backtracking, which is where you would go back down the path that you came. However, as you're doing this, you're going to do sort of the pre-order style in that you're going to keep track of where you've been so that you don't print stuff twice. So in this case, we started at S, so we printed out because we've been there. Then we stopped by C, and then we went to D, and then we hit our wall. What is the time complexity and the space complexity? Of all of the ones that I'm going to be talking about today, is B plus E for your space. For your time complexity, you're visiting every single node at least once, so potentially N. That's just the best thing to do. Okay? But if you're more interested on the technicalities of it, I can post a link for you guys on chat. And I think at the bottom they have a bit of a discussion on the time complexity, where they do say that B plus E, where V is the number of vertices and E is the number of edges, and that's your time complexity. And for space, it's going to depend on how you store it. Remember that adjacency matrix is B squared. Adjacency list is going to be B times E or B plus E. Let's see which one makes more sense. It would just be E actually, plus B, E plus B, yeah. And then if you're storing it with pointers, then you're just storing everything once. So I suppose V, if you consider just the space of the nodes, not the edges. So anyways, back to this. As I said, you go to D, and then that's when you hit that wall and you start to backtrack. So then you're going to come back from D. Oops. to C, which you've already been. And at that point, you're not going to go back to S because you have other choices to go and you're greedy. So you try and take them. You hope for the best. You don't go back to the beginning. You commit down this path that you've taken. So from there, let's say that we pick F. All right, so you pick F. So we get to F. We print it out because we have never been there before. And then we keep going. There's only one way, and that's forward. And so we get to G. That's all good, you know, we're visiting new places, you know. It's like we're on a road trip because of coronavirus, you know. You take a road trip because you have nothing else to do, and then you're just trying to visit as many places as possible. And if you take a path that you haven't taken yet, why not? Time to discover this brand new town. And so you get to G, and from G, you go this way. And why would you go to S? Well, think of it this way. You take this road, you know where it's going to take you. If it said a sign like, this is the way to S, then you wouldn't have gone there because you've already been to S. But say you don't know that. So you just take the road and then you arrive to S and you're like, oh, I got back to where I started. But does that mean that you've gone to every single spot in the map or in the graph? You know, map if you're traveling. I don't want you to confuse it with hashing. And that's not necessarily true, as you can see that visually. And the way you kind of decide that is you're like, no, let me go back the way I came. So back to G. And then you see that there's more paths available to you. And so you go to G, or sorry, to H. And you keep going. Forward is the only way. Progress. And then from E you get to C. And you're like, oh, wait a second, I already been to C. So I'm not going to keep going further. I'm going to go back. And here's the thing. Suppose that in C, you had other ways to go. Like suppose in C, you hadn't gone to D yet. You don't just go to D. You already assume that since you were at C, you want to back down. So you don't try to go into a different direction. Okay? You back out. So you back out to E. You back out to H because there's nowhere else but back. You back out to G. And then from there you back out to F where you came from, and then you back out to C, and now you're like, oh, okay, there's nowhere else to go. So then you back out to S, but then now that you're here, you can go to A. So that's a little bit tricky there because I could have gone to A before when I came back to S from G, right? But that's not really how the algorithm works. In that case, what you want to do is you want to back out until you came to that the first time, the way that you came the first time, and then from there now you can go to A or B. Okay, so this will make more sense algorithmically in a second. So as I'll defer your coding question on that until I actually show you the example algorithmically. Now, why is this so easy to do with recursion, for example? Just the same way that it's very easy to do the recursion stuff for traversals. Or sorry, it's very easy to do traversals with recursion. How do you decide which child to visit first? Arbitrarily, just one that has not been visited yet, as you'll see in a second. Yes, you can recursively loop through all the non-null nodes. That's correct. So it's the same way as traversals. You know, you just code something that says, run through the list of children or the list of edges and pick one that you haven't visited yet. And so you go in there and you pick it and then you just keep going as deep as possible until you hit a wall. And if you do, then you go back and you try going in a different way. How do you say until you haven't visited yet? Well, you simply recursively call on every single child. Now, here's the one thing about recursion that could cause problems with this, and that's if there's cycles. Now, I know what you're saying. Cycles are more of a directed graph thing versus undirected, right? Because there's always cycles in undirected graph. I'm talking more about cycles in the sense that you can go back to a node that you started from after you visit at least one other vertex, such as going back to S after visiting, for example, C. Because if you go from S to C, then you can go C to F and F to G and then back to S. So that's a cycle in the sense as it would be the same to say S to C and C to S. That's a cycle too, but that's not really as important as the other kind. Because that kind we can detect to make sure we don't go back the way we came from. But to have a cycle like that where we visited multiple nodes, is very hard to sort of avoid with recursion. And so why didn't we run into this problem when we were doing the inception assignment in 202? And that's because there was no circular references in our dream layers. And so we got away with that. But here, as you can see, we wouldn't get away with that. So if you just copied and pasted your solution from inception assignment, you'd see that this thing would recurse forever. And so how do we stop that? We need to have memory. And memory in the sense that we need to remember the places that we've been. And so the easiest way to implement it is with a Boolean array that keeps track of where you've been. And then you can just stick to recursion and not use your stack. Of course, the other way to do it, the, I suppose, better way to do it, because with recursion is very expensive with all the function calls and everything, is to actually use a stack data structure, and then you can make this code completely iterative, so no recursion, and much faster as a result of that. Okay, so how about I show you that version then? So as before, we are going to keep track of our stack using a little stack there. And in this case, we are going to say that this is the top of the stack. And I know bottom's not a thing, but I'm going to put it anyways, because otherwise I'll get confused. Why would you use a Boolean function to determine where you are and not a void function? No, you're not determining where you are. You're determining where you've been. It's replacing the concept of memory, that you don't want to visit the same town twice because you remember you already visited. That's what you're trying to use the Boolean array for, not function. So you'll see in a second here. In fact, let me go ahead and write that down. Okay, so that's going to represent our Boolean array of visited. However, I think it might be faster if I copy and paste it from the other class. The one that we did for, oh no, that doesn't look pretty. So never mind. We'll just do it by hand. You just have to, I don't know, I just had a quote come into my head from The Dark Knight Rises. You just have to imagine the fire. A, B, C, D, E, F, G, H. A, B, C, D, E, F, G, H. And then we got an S. Why so serious? That's not the right movie. That's the other movie. Why did that come to my head? I guess because I was thinking like you just have to imagine the other picture. I don't know. But okay, so this looks much smaller than the one before because this one's nice. Okay, so we got our Boolean array. So this is a Boolean array that we also call our visited array. And it's basically our memory. We got amnesia. We don't know where we've been unless we write it down. This is this is like memento tier. So because we need to write down where we've been, where we've investigated, we are going to write it down here. So that way next morning when we wake up, we remember where we've been. And by next morning, I mean the next edge that we take. Okay. So we got our stack over here. Remember that stack of plates? And then we are going to have our output. And again, these breadth first search and depth first search traversals are a way of printing the graph. And even though there's no assignment on this that you have to do, you may still have to do this algorithms in the test. But more importantly, when you're doing assignment 11 and you want to test if the thing is working or not, other than printing out the adjacency matrix or list, you can print out a traversal and see if it looks right. So they're useful. They're also useful for printing out sort of decision trees of what you want to do. Like if this was a game and these were your choices, that first search will kind of tell you a one way of solving it, I suppose. So okay, ideally we want to have the least amount of shall we say repeats, where we go to the same place that we've already been before. There's one way to do this. Like for example, we could have done this. I'll do it real fast. We could have done something like this. And then from there we've already kind of, in fact, maybe not even, maybe a nicer way to do this would be like that. Go there, back out, go there, back out, go there, back out, and back, and then here, right? We could have done something that has the least amount of backtracking, but depth first search doesn't care about that. We don't care how much time we waste backtracking. It's a very simple algorithm, again, doing this in the sense of doing that. So don't worry too much about trying to make it efficient in that sense. I'll give it a second because it's lagging a little bit. By the way, how's the stream? Is it better than before? I know I did some modifications and tweaks to the settings with the help of Kawa and others to try to make it a little bit better. So hopefully it's better now, way better. I'm glad. That's good. Either way, the YouTube recording is still being recorded on the top quality, so that's always going to be better. But live is good because you can interact, and you can always go back and see pieces later on YouTube. I did drop the resolution to 720p. Yes, I did. However, the YouTube one will still be 1080p. I do think that 720p, while yes, it's slower on the stream, I don't think it makes it harder to read things. But if they do, let me know. I will experiment again in 1080p. My shirt glitched with the background. I did notice that. That's because I'm wearing greenish shirt. Not the best choice when you're using a green screen. So that's my bad. In fact, I'm a little bit ghostly because of that. But yes, I didn't think about that until until the camera came on, and I was like, oh right, I'm not supposed to use green with the green screen because, you know, the chroma keying can't decide what I am. That's why this shirt, I know this shirt looks weird, but it's actually green. Maybe you've seen this in person when I'm wearing this, but like it's a green shirt, so it's a very bad. At least I'm not a full ghost. That'd be weird. But yes, okay. And that's just the white parts. Like if we go back to the Death Star, you can see that it's a little bit ghostly, but you can kind of see the green on it. So yeah, okay. So we start out at S, so that's going to be the first thing that we output. And then just like before, we're going to add all the edges coming out of S to our data structure, in this case a stack. And so it doesn't matter again which order we add them on, we're going to stick with the alphabetical order. However, this being a stack, they're going to get order in a little bit of a sort of, they're going to look the same as before. You know, it's still going to look like A, C, and G. You know, it's looking the same as before. However, before, if we were to pop something out of it, because it was a Q, you pop out the A. That would be your DQ. Here, if you pop something out, it's not going to be the A. It's actually going to be the G because it's the top of the stack. So already things are going to be a little bit different. But that's good because we're doing depth first search. We're not doing breadth first search, right? We're trying to mimic the call stack from recursion. Okay. And so we go ahead and we mark S as visited. And yet again, as before, even though I didn't say it, you're only adding things to your stack that have not been marked as visited, which in this case, nothing has been marked as visited with the exception of S itself. Okay, so now we're done with S, and now we can go ahead and pop the next thing that's available in the stack. And so that's going to be G. And in fact, I'm going to draw here kind of what has happened. Okay, so I'll draw and it'll keep it updated. So we're going to pop out G, get it rid of it from the stack. And the first thing we're going to do so that we don't forget is we're going to mark it as visited in our visited array. And now we're going to add all the things to the stack that have not been visited yet. So from G that are connected to G. So that's going to be F. Oh, failed. That's also going to be H. And not S, because S has already been marked as visited. The other ones have not. H and F are not visited, but that has. So you only add those two. And at that point, you can consider yourself to be done with G. The next thing that we're going to do is we're going to pop out the next thing from the stack. So that's the H. So that's basically us going there. We go ahead and before we forget, we mark that as visited now. And then from there, we're going to add all edges or all the out degree. So the out degree of your vertex is going to dictate how many checks you have to do. So in this case, the out degree is 2 because there's 2 things coming out of H. You check them, you check G. Do you add G here? You do not, because it hasn't marked as visited. So you don't have to add it. Do you add E? Yes, you do, because you haven't visited yet. So you go ahead and add it. And that's it. Nothing else. No G, because you visited. E, because you haven't visited it. Cool? Moving on. Guess what? We do E. Because it's the top of the stack. So now we are here. Mark it as visited. And then from there, go ahead and add all the edges. In this case, we have two, C and H. H has already been visited, C has not. So you just go ahead and add C to it. Okay, you're good. All right, let's pop the next thing. Turns out it's C. Okay, so that is like us basically going here. There we go. All right, that's a big one. That has S, F, E, and D. Both S and E have already been marked as visited, but D and F have not. So we're gonna add them to the stack here. D and F. And I know what you're saying. F has already been added. That's okay. Don't worry. Just like you didn't have to worry with breadth first. All right, and we forgot to mark C as visited, but we're good. I think we got everything before that. I do want you to notice that it essentially the output of this and your visited array look pretty much identical. So I'll leave it up to you whether you want to keep this or not, you know. But I still would. Whereas with breadth first, it does not look identical. So yeah, okay. And you can use a hash table instead to make it all of one time. Constant time, for the most part, without collisions. Okay, so from there, we said we were going alphabetical. So we're going to go ahead and go to D. So, oh, what? Sorry. I forgot I was doing the algorithm. You don't go to D. You go with whatever's on top of the stack. So F. Mark that as visited. Okay, so that's us going here. And from there, we have two choices, C and G. Both of them have already been visited before, and therefore you don't add either of them. So at that point, you are basically not adding anything. And so what do you do in that case? Well, you make sure F is marked, and then you just pop out the next thing from the stack, which is D. Oops. And so here's like the smart thing. You're like, whoa. You're like, hold on a second. How did we go from F to D? That's not backtracking. Technically it is, because like, what did really happen? What really happened is, you were at F, you came back to C because that's what added D to the stack. And then once you were there, you actually moved on to D. Oh, I can't use that color because that's taken. Let's use red. So really, that's what happened. You came back to C and you went to D. The stack takes care of doing that. So that's kind of cool. You automatically knew you had to go to D. So that's neat. That's like the unwinding of the recursion if you're doing this recursively. Okay, so now that you're at D, you can mark D as visited, and you can add anything that has not been visited to the stack. Which in this case, the only thing you could add is C, but it hasn't been visited, so you add nothing. At that point, where do you go? You actually go to F. So you pop this out, but here's the thing: you've already visited F before, so you're not going to add it to your output. And you can see that in two ways. One of them is you can look at the output and you can search for letters that you've done. Or you can use your visited array, which if you make a hash table is all of one time, and you don't go ahead and add it. So you're not going to add output out that you already added, because you want to add a letter twice. And so therein lies the advantage of keeping this little Boolean array as a hash table, because it's much faster than running n time searching in your output to see if you've already printed out the letter F. So that F got discarded into like a little garbage can here. You know, F in the chat for F. All right. You guys are really quiet on the chat. I hope you guys are not just like watching anime and not putting attention or something. All right. So, yeah. So that F, us going to that F is kind of like what we really did there is as follows. We were at D. You know, let me pick a little bigger circle. We actually did this. We went all the way back here to that F. And how did we get to that F there? Well, we were from G. And then we didn't print it, so then we went back to G again. And now we're actually going to go back, technically, all the way to S, and then go to C this way. Because we're going to pop out to C, but we're going to notice that it's already been visited, so nothing's going to happen. So from there, we're going to go back to the S again, and finally we're going to go somewhere new by going over to the A, which is going to be the next thing that we pop out. In this case, it has not been visited, so we're going to mark it as visited, and we're going to add it to our output. And we're going to add in things that have not been visited there. So we have two choices. We have B and S. S has already been marked as visited. B has not. So we're going to add B to our stack. At that point, we're done with S, or sorry, with A. And so now we're going to try to visit the next thing, which is going to be there basically. So pop that out. You could preemptively stop the algorithm at this point. Once everything has been marked as visited, you can just call it a day. But if you want to be thorough about it, or if you don't know, which is well, I'll get to that. I'll talk about that in a second. Let me just finish first. We get to B. We add anything to the stack. At that point, we're done. We go ahead and look at the stack, pop the next thing out, but the stack is empty. That's the real sign that we're done. That's the real sign that we're done is when the stack is empty and there's nothing else to do. So that's kind of like technically what happens there is you go back to S, right? So as you can see, a lot of that is sort of low-key mentioned, that path, but really you don't care about that because this is correct. You know, this is actually correct. And so here's the thing that I was just going to say about this. With the depth first search traversal, the cool thing about it is that you don't need to know how many nodes or vertices are in your graph. If you're just in the blind, like I said with driving, you're in the blind of what exists in there. You don't know how big this Boolean array is. You can build it as you go, or you can do the thing I was saying, which check your output to see what has already been visited, right? And so if you have this Boolean array, then yes, the moment this Boolean array is full, you can call it a day. But if you don't know what's in your graph, you don't know how big your graph is, so you don't have this Boolean array readily available, then you can build it as you go, or again, you can just use your output to check whether something has visited or not. And ultimately, the real sign that there's nothing else to go through is going to be your stack. Furthermore, suppose that we had an additional vertex here that was like T, and it was not connected to the rest of the graph. You know, T would be here, and it would not be marked as visited, right? And because it's not marked as visited, it turns out that you could, if you didn't decide the stack being empty as the end of the algorithm, you would never finish. You'd be just waiting and hoping that there's a way to T, but there's not. So really the best way you can indicate it is when you finish adding everything that you need to add with the current node, which is B in this case, and then you go to the stack to pop the next node to look at, and there's nothing there, that's the real indication that you're done. And any node that does not get printed in your breadth first order traversal, or even your depth first order traversal, either of them, you can safely assume that it's not connected to the rest of your graph. If we were to do a breadth first or depth first search traversal on starting with T, you'd see that nothing would get added to the data structure, queue or stack. And that would be the end of that. Questions before we move on. So, when you use depth first search as opposed to breadth first search, when do you use? Depth first search is going to kind of give you how far you can go in one path to try to see the entire graph. And you will be able to, but at some point you're going to have to backtrack. That's one way of sort of looking at a graph. That's your level of order. Breadth first, or sorry, your traversal, like post and in pre. Breadth first search is kind of giving you sort of the, without considering weights, it's giving you sort of the overview of what your graph looks like in terms of who's closer to you. Breadth first search will print things out sort of in a distance-based scenario where weights don't matter. It's just a matter of the number of edges to get there. So it'll print all the nodes that are closest to you, and by you I mean the starting node, first. And when it finishes printing those, it's going to print the second layer. So you can think of it like a circle. So breadth first search kind of works like this, in that this is the starting node, and then the first circle is the people that are connected to that node directly. Like, these are your closest. If you're thinking of a social network, these are the people that are closest to you and that you have them as a friend on the network. The next layer are the people that are friends of your friends. They're not connected directly to you, but you can communicate with them if you tell your friend to message them. Finally, the third layer, if we had one, will be the friends of your friends. So that means for you, they're two connections away, which means your friend, or you have to message your friend, and then your friend has to message their friend. You have to message your friend, sorry, and they have to message their friend to get there. Yes, sorry, I have to think about that for a second. So first you have people you can contact directly, and then people that your friend can contact directly after you tell them to contact them, and then people that they have to contact additional levels. So the deeper you go, that's breadth first search. It's useful for representing that kind of connectivity stuff. Depth first, trying to greedily go to a graph or a tree to get to the solution as quickly as possible, but usually very inefficient. Depth first search when you want to find something, breadth first search when you want to find shortest path something. Shortest path we will talk about with Dijkstra's. So don't get confused with shortest path. How much of delay is there, by the way? Like, you can see it by looking at your own messages on the stream. Like, see how much of a delay there is on the stream right now. Hopefully it's not too long. So any other questions on depth first search? Like 15 seconds. Oof. Okay. I tested it yesterday and it was like 3 seconds. I guess the longer the stream goes, the slower it gets. But it's not too bad, yeah, I suppose. Okay. Moving on to topological sort then. Oh yeah, that's true. If you have a really long delay, you can try refreshing the screen. It might help a little bit. It's not going to be the cure to all ills, but it will help a little bit. Time for a new algorithm, topological sort. Now, before you get excited, we're not learning a new sorting algorithm today. I kind of wanted to use the same graph, but I suppose I'll use a new one. So we're not learning a new sorting algorithm per se. It's just another way of per se traversal. But this one only really applies to directed graphs. It can kind of apply to undirected graphs, but it's weird. So yeah. Okay, I will remove this edge and then I'll add it later. Okay. Yeah. For now, we'll put it like that. Okay, so here we have a directed graph. We don't quite know if there's a cycle, but we have a graph. Topological sort is a algorithm that you can go ahead and print the graph, but there's one rule, and that is that every vertex that you print has to have, shall we say, they're going to be printed in the order. How to say this in an easy way to understand, nicely digestible way. I mean, I can show you the algorithm and then you'll be like, oh, okay, I understand. But it's kind of hard to describe. I suppose every vertex that gets printed will only get printed after it has no edges coming in, so no end degree. And how do you get rid of edges? Every time that you print a vertex, you're going to delete it from your graph. And so all the out degree edges coming out are going to get removed as well. So, in fact, maybe before we do the big example, let's do a tiny one. Suppose you have that piece of the graph, okay? What topological sort says to do is you're going to have an output, which is going to be, again, sort of a traversal. And it's saying you cannot print B and C first. Why? Because they have an edge coming in. And before you can print out anything with an edge coming in, you have to print whatever that edge coming in is doing. So in this case, A has no edges coming in. The in degree is 0, the out degree is 2. So because the in degree is 0, we can print out A first. And after you print out that vertex, you erase it from the graph and you erase all edges that are coming out of it. And because there's no edges coming in, you don't have to worry about that. So now, both B and C have no edges. But suppose that the graph is a little bit more complicated. Suppose that there was also a line going down like that. Okay? In this case, when you delete A, you have two vertices left. One of them has an in degree of 1 and the other one has an in degree of 0. The in degree is, again, the edges coming in. B has no edges coming in now, but C does. So you have to print B first, which will then get rid of it and get rid of any out edges. And then you have C, which has no in edges, so you can print it out. And you're done when you basically either deleted everything from your graph, or there's nothing else that you can do because no other vertices have in degree of 0, in which case it means that you found a cycle potentially. So this topological sort is a good way of testing a graph for cycles, a directed graph. Make sense? I think it makes more sense to give you an example like that. I will go ahead and post the Geeks for a topological sort. By the way, what do you call it? Pitch or something? I don't know. I'm doing a machine learning lecture at 2:30 p.m. I'm streaming it for the other class, the CS 458 or something. I don't know what it is. You're welcome to comment that. We will be talking about support vector machines both Tuesday and Thursday at 2:30 p.m., which also means that I will have to make sure I end the stream around maximum even after lecture office hours, like 2, so I have enough time to switch gears and get ready for the other lecture. Okay, so the algorithm that I have for topological sort is to pick a vertex with in degree of 0, which means it has no edges coming in, output it, so as in like add it to your output, and then remove it and all the edges that are coming out of it, and repeat this algorithm until all vertices are removed. That's it. So this is quite trivial in that sense. Let me copy and paste this graph. You guys are very quiet today. I don't like that. I feel like I'm talking to a wall. Is it called a sort because it prints nodes in degree in ascending order? Yeah, you can go with that as a reasoning for it. Nothing on Discord either. Oh, by the way, if you're scared of your question showing up on chat, the alternative is Discord. That's not on chat, so you can still ask. So if you're ashamed of your question, which you shouldn't be, you can always ask a question on Discord, and it'll still be. And I'll keep it anonymous, as no one call out whose name it is. I'm sorry you went a little bit too fast. How do you do it? Do you say it's a 0 sorted then delete it? Don't worry. We're about to do a full on with this graph. I'm gonna do it, and then let's see if you get it. All right. Busy dabbing on the haters. How do you do the dab like that? Okay. All right. So we're gonna do our output, and so what we'll do is as follows. We're gonna pick any vertex that has an integer of 0 as our starting point. That means that there's 2 starting points in this graph. It could be A or G. How do you pick one from the 2? Arbitrarily. We'll go alphabetical. So I know there's a way to make it invisible on the screen. Oh, I don't know. But anyways, so in that case, we're going to go alphabetical with A. But we can, which by the way, should tell you that just like depth first search and potentially breadth first search as well, there's more than one output that is a valid breadth first search, valid depth first search, or valid topological sort. It depends on when you start, essentially. So where you start matters, and even then, if you start from the same spot, there may be more than one divergence, as you will see here. So in fact, maybe I'll do 3 of them. Okay. So we start out with A, and so we go ahead and I'm gonna just highlight the ones that I take care of. So we're gonna go with A. We're gonna delete all edges coming out of A because of it, and we're gonna add it to our output. Okay. And so there you go. So now that you're at A, you actually have 2 choices. One that has opened up recently, and that is C has no edges coming in, and G still has no edges coming in. At this point, you can pick either or. So that's why I said I'm going to do multiple choices here, because you only have to do one. But I'm just trying to make a point that there's more than one answer, which is of course awesome thing when you're grading a test, right? Like I feel bad for the TAs for that, but such is life. Okay, so in this case, we're going to go with C. Okay, for this first sort of attempt per se. When we do C, that means we're going to delete all the edges coming out of C. That's an out degree of 3. And so now that opens up a couple of new possibilities. We still got G. G's just waiting there, chilling, ready whenever you want. B is now available because it has no edges coming in. And D is also now available. So let's go ahead and go with B. So already you can see that if we had gone instead of with B with like G, then that would have been a traversal there. We could have also gone with G down here. So as you can see, all of these would have been correct, but different universes, right? Alternate timelines where the stones were destroyed. You know, Avengers. Okay, so we're going to go, in this case, with B, which means that we're going to delete this edge. However, in none of these alternate timelines can we ever do E first, because E requires to get rid of both G and D. So in any timeline that we think about, G and D must have been printed in our topological sort before E can go. So it's impossible to see that, to see E printed before G and D. Okay? People are asking when is 11 due? Check Canvas. I don't remember now, but I think it's due the Sunday, a week from today, from yesterday, or was it Sunday? I don't know. That's why I want you to get started on it, and then just throw in the minimum spanning tree stuff at the end. What is the little asterisk? I don't know. Is it like some censoring system? I guess. I don't know. Who knows? Anyways. Miss the opportunity for May 4th to be with you. Yeah, but I think that I'd rather have people do the final project, which means you have more time. I mean, actually, that's a good point. So I could make the assignment due later because you don't want, then you won't have anything to do that Tuesday, that Monday, I mean. So I could make the assignment due before class time. I could do that, but that would require me making it not due before midnight, and people get confused. So maybe I'll make it due Monday night. I might switch it to that then, because there's no gain, because we won't talk about Dijkstra's for sure this week. So, oh no, but it's due May 3rd. Hold on, what am I thinking? That's okay. No. Ignore what I said there, because actually, we will talk about minimum spanning trees on 23rd, and then we have next week to talk about Dijkstra. So actually, that's fine. I did leave it like that because then it actually overlaps with the final assignment. So yes, I thought it was the 27th for some reason, or 26th, but no, never mind. You guys have plenty of time. Yeah, this is Edge of Tomorrow too. It's not Star Wars. Imagine liking Star Wars in 2020, right? No, I do like Star Wars. Okay. So, let's go ahead and get this done. We got 5 minutes, and I want to get this out of the way. And I actually wanted to start talking about minimum spanning trees, so that you can kind of get going on the project. But you can do the project already, except for the minimum spanning tree stuff. Assignment 12 is indeed the final project. That's going to be Dijkstra's surface path, and it's going to be worth over 1,000 points. This one's due 7777, or sorry, 3 sevens, not 4. And then the final one's going to be worth anywhere from 1,000 to 1,600 points. It's going to be like 1,200, maybe 1,400. I don't know. How about we find assignment B? Not as bad, actually. In fact, I think it's not. In fact, maybe I think this one's a little bit harder. This could have been the final project, to be honest with you. But so it might end up being that might be just like it might not be that much. I don't know. But yes, I did say that, and it has been posted already. That's a TRICE assignment. There, I guess, announcements. So look at the email that I sent with all the things, including whether about summer 3 and things like that, which it's undecided yet for summer 3 class. So yes, 19. But yes, there's a try programming assignment based on the bonus try lecture that I recorded and is on my YouTube channel. Don't forget to like, follow, subscribe. But but you can watch that and then do the PDF. Read the PDF on it and do it. But it has been posted. It is due in a week, I think. And it's not that bad. Make him do it in assembly. Make them do Dijkstra's in assembly. I don't know. How about you show? How would you show us your implementation that you did for Dijkstra's from my 302 class, Kawa? Huh? How about that? I want to see that. So, anyways. Let's get to that topological stuff done, and then we can save the questions for later. At least non-topological sort of questions for later. Yeah. So yeah, that's right. The TRICE is due pretty soon, so you better get going on that. It's not a hard assignment though. So okay. So in this case, we're gonna pick D. Actually, no. Let's pick G first. I don't know why, but I just felt like doing G first. At that point, no other choices have opened up, but we still have the D choice. So then we take the D choice. Okay. So unsubscribes. Interesting. Okay. So from there, we've got E and F to go. And so we basically only have 2 choices that are opened up after getting rid of D, and so we can pick one or the other. So we're gonna pick E. And if there wasn't a 15-second delay, if we were doing this in person pre-Corona times, I would have asked you guys to pick for me. But doing that in the chat would have taken us 15 seconds per node, which would have been too long. Are you guys testing like the way the censoring system works or something? I don't know. But yeah. Okay, so that opens up nothing. So we can do F now. That opens up T, which then opens up S, which opens up N. That's basically like that and that. Okay? That's topological sort. Same time complexity as the other two, V plus E. I put it on top of the page as well. So what? The word unsubscribe is censored, I suppose? Oh, we put that? Yeah, but it's still posted. You put a message. But I guess that's a useful thing. I don't know. I did add... Oh, well, I added that if you add exclamation point, it shouldn't show here because that's a bot command. Or if you were to have a bot in here, it wouldn't show that. Or I should say it shows as that. Yeah, I can see that. I have them both open so I can see chat. But yeah, that's topological sort. You can do another one. You could do the same thing, but you could have picked everything else different from here. So like, you know, if I wanted to have an alternate one, alternate timeline per se, I could do this. And then everything else will be the same. So there's more than one answer, just like there are with depth first search and breadth first search, okay? How does this sort? Well, it sorts in the sense that any in-degree thing will appear first. But then you're like, well, G had 0 coming in from the start, and it didn't show up until the end there. Yeah, but at the time when we printed those, then other things were removed before. So I suppose that's where that comes from. That's all I got on that. However, the trickiest one to implement, actually. I was looking at the implementation for this. I've actually never programmed myself topological sort, I think. I can't remember. I might have at some point, but I forgot. But I was looking at the implementation, and even the Geeks for Geeks people say, like, look at how depth first search works with the stack, and then this is sort of an alternative to that. I think that the easiest way to do this, if from if I were just to tell you what I would do, is maybe there's lag, but well, is get your adjacency list out. Figure out what has nothing coming into it, which is kind of like the opposite of the adjacency list. So you can look at the adjacency matrix as well, and look at the 2 column. You know, remember the from and 2 column. So maybe I can pop one out right now. Here, let's see, when did we talk about those? Right here. Okay, so we have the 2 column, so we can see what's coming into a node if we look at the vertical column. Okay, like for example D. And so here's the thing: look at the column there that has nothing coming in at this point. Print that out as the next node you're visiting, and then once you do that, delete the horizontal column for that node that you just printed out. Okay, so maybe I can, yeah, we can go over for like a minute or two or whatever. We have anyways for like most times anyways. I'd like to show you how that would work. It's just going to be such a big graph, big scary graph here. So we got A, B, C, D, E, F. How about we do let's do an easy one, okay? Let's do like a subset. Oh, by the way, one other thing I wanted to point out about topological sort, it will tell you if there's cycles in your graph. How do you know that? Because suppose that I switch this over to be this way. Okay? You have a cycle between C, D, and F. And because you have a cycle, it will be impossible to print out the topological sort of that graph. So if we have this, and then we have like A here. Okay, topological sort, print the A out, gets rid of that. At this point, you can't print anything else out because they all have an edge coming into them because it's a cycle. So whenever you can't get the topological sort of a graph is because there's a cycle. So it could be used as a cycle detection algorithm per se. Let's see some questions. Why would you want to sort that? I have no idea. Well, cycle detection is used, but do we have to implement topological for an assignment? You do not, but you need to know for the test. Just in the same way that I did it. I'll give you that and I'll make you draw it and erase edges and print out the ordering. It's just a useful thing. I think it's another way to slowly get you comfortable with graphs. So anyways, I'll do this really, really fast. A, B, C, A, B, maybe a D as well. C and D. And then maybe D goes here. Okay? Actually, there. So, this being a symmetric, because it's undirected, we're going to have all ones here, basically. And then, okay, so, or sorry, not it's directed, not undirected, what did I say? So this is our to, and this is our from. So from A, we're going to B, and we're going to C. From B, we're going nowhere. C, we're going to B. And then D, we're going to C. Check me out, chat. Tell me if I missed anything. We got 1, 2, 3, and 4. 1, 2, 3, 4. I think we're good. Why can you not print the topological sort of the cycle again? Yes, there's no vertices within degree of 0. Yes. So like if you have a cycle, it means that it's like a snake eating its tail. And so the rule says that you have to be able to take the tail of the snake. But because it's eating, you cannot take a tail that's already been taken. So you can't grab a tail because it's eating itself. So you can think of it that way. So it's like, oh, I don't know what just happened there. So it's like, you know, each node here has an edge coming in. It's impossible to delete an edge because you need to have a 0 degree. You have to break a cycle somewhere. And now you can go ahead and delete one at a time and you're good. But with a cycle, you cannot. So cycle detection is a use of topological sort in a way. Hashtag checking it out. Okay, interesting. So, how do you implement this if you just want to forget about that stuff and the topological sort on Geeks for Geeks and whatever? The easiest way to do this is you just go ahead and, first of all, don't worry about going to yourself, because like if you think of a following graph, what's the topological sort of this? Easy, DF, right? But if you think of D as going to yourself and F pointing to yourself, then you got yourself like mini cycles and your whole thing breaks down. So not good, right? So get rid of all of these ones here, and now you have all your edges, right? So the way you can do topological sort here is you're going to look at the vertical column. Fail. And any column that's empty, so these two, you can go ahead and print out first. So pick one. So you pick D. Okay. Picking D, and I guess I'll leave it before and after. So we'll copy this one time and paste it here. So this will be before and after. Picking D means deleting this edge. Okay? How do you represent deleting an edge on the graph? Horizontally, you go ahead and do that. So horizontally, you're going to delete all lines there, which means you would delete the 1. Okay? In this case, I'm just going to... No, I don't want to cross it out. I'll highlight it in red. Red means deleted, okay? So now you have only one choice. That's empty. And that vertical column that's empty is A. So you go ahead and do A then. So that would be the equivalent of deleting these two edges. And keep track of your output, of course. So D, A. Okay. How do you delete that horizontally? Easily. Just go ahead and delete horizontally these, which means these are now gone. And as you can see, the C column has nothing left in it because both the ones are gone. The B column still has a 1 there, the C to B. But the C does not. So we can go ahead and get rid of that. Bam. Eliminated. Fatality. And then that, because we did get rid of C, we can get rid of horizontally of that. So that would be this, which would indeed get rid of... Oh, I used that color already. Use brown maybe. Which does make that column empty. At which point you can go ahead and print it out. Okay? 26 people watching. Oh, yeah. But anyways, that's all the A grades are here watching probably, and all the C grades and lower are not watching, so that's life. Or they have class, who knows? But the YouTube channel's recording will be up, so yeah. I could force you to watch by not having a recording uploaded, but I think that would be unfair for people who have a real excuse to not be here. So, well, it feels bad, man. Okay, so there you go. That is how you would implement the easy way without the complicated stuff on a topological sort. Easy mode. Of course, it doesn't work if you don't have an adjacency matrix, but if you have an adjacency list, you can convert it very easily. If you have pointers only, then, you know, good luck to you. Be blessed. All right. Yeah, that also too, that there's higher quality. Okay, so I think that's going to be the end of this. I will talk about minimum spanning trees on Thursday. That's going to be a beefy lecture because I'm going to talk about 2 algorithms to solve minimum spanning trees. And to be able to talk about the second one, I have to talk about disjoint sets. So worst case scenario, if we have, if I don't get to both, I will at least talk about one minimum spanning tree algorithm so you can do your assignment on that one. And then the other one we'll save for Tuesday. And so on. Or I'll make it a bonus lecture, I suppose. But yeah, I don't know, I've never tried Mixer, but I was watching, I never watched streamers, by the way, but last night I was watching Ninja on Mixer for some reason. And that was interesting. Can you build a graph from a breadth first search or depth first search, like how you could build a tree, a binary tree from 2 traversals? Can you build a graph from breadth first search or depth first search, like how you can build a tree from 2 traversals? Oh, well, ooh, that's a really hardcore question. That's like an analysis of algorithms question, frankly. You know, I'm going to preemptively say that you would need more information than just that, because here's the thing. First of all, we're assuming an easy mode. We're assuming like unordered graph, which means no arrows, unweighted if you want as well. Can you build a tree, an accurate tree, from a level order traversal and a post order traversal? Can you? And I'm not 100% sure. Maybe there's an algorithm. I tentatively want to say yes. Here's the thing about the graph. As you're telling me, I would say no. However, you can do a little bit of modification to your breadth first search traversal to have higher chances of being able to build it. First of all, you want to separate the levels or layers, because as you have it now, breadth first search or depth first search, you never mention in the output when you're backtracking. Same with breadth first search, you don't mention the different layers. So if I was able to put a comma indicating like this is where layer 1 ends, this is where layer 2 ends, and so on, if we could do that with breadth first search, that would give us far more information to be way more useful. And then we could potentially kind of use depth first search to build the rest of it. The problem is, again, it doesn't tell us when we backtrack and if there was a path there. You know, I could build other graphs that would give me those results. So I'd say it would be very, very hard. There's definitely no clear and present algorithm that I can think of that can do that. But that does bring up a pretty good question. That's definitely something that they should look at in analysis of algorithms. It actually makes me want to Google that too. So I'll investigate, and then I'll let you know in the next lecture what kind of algorithms you can do to build a graph from a traversal. Because remember, graph is much harder and more complex than a tree. With a tree, we have the idea of left and right. You know, with in-order traversals, you got to go left first, and you got to go right, that kind of thing. You know all of these things ahead of time. These are not givens in a graph. It's far more ambiguous per se, which makes it a lot harder to do. But if we knew the levels, then, you know, yeah, we need more information basically. When do you want to use topological? So what was your motive? Like I said, cycle detection. That's one usage of it. If by the time you're done doing a topological sort, you find out that you weren't able to get everything taken care of. And here's the thing, topological sort, it doesn't matter if your graph is not connected. If your graph is not connected, for example, this, suppose you got that as your graph. You can print this, then this, then this, and then this, or you can print out this, then this, and this. No problem whatsoever. So there's no problem with topological sort of printing graphs that are not connected. What topological sort is finding is cycles, and it's very effective at that. That's what you can do. If at the end of topological sort you can do. Oh no. Wait, what did I do? Oh, did it die? Are we back? Is it live? Are we good? Are we good? Are we good? I got a little bit worried there. I started to see an explosion in chat. Of panic. And then I looked down here and I have a little color, red, yellow, green, showing me the bit rate. And it went to 0. It's right now it's actually at 600, and now it's 6,000. So it even said I went offline. That's kind of scary. Hopefully that doesn't split the video into 2. But if it does, then it's okay. We had most of the thing now. Yeah, it's kind of iffy. It's at 148 right now. Your offline thing came up. Oh, that's horrible. Sorry, guys. Sorry. At least that was the most responsive we had from chat in a while. Yeah, because it actually, even though the upload died, the download was still good. So all your chat later, like you can see the flow of chat in my reaction of like, oh snap. So we even had the viewer increase to 34. So yes. Anyways, I have no idea where it ended up before the cutoff, so I'll just say the last thing I was saying. The answer to the question is topological sort is useful for cycle detection. Very effective at that. If things are unconnected in the graph, doesn't matter. It'll still look for any sort of cycle. And if at the end of a topological sort, you have not printed out every vertex in the graph, then you have found yourself a cycle in the remaining vertices. So that's the primary usage of topological sort. So topo sort, as some people like to abbreviate it, is good for cycle detection, which has its own usages. Whether like what cycle detection is useful for, tons of things. We'll talk about it other times. All right, questions before chat ends. I mean, stream ends, like intentionally ends, not just dies like before. Corona. Hashtag Corona. Oh, this doesn't have the Twitch chat on it. For the extra credit assignment, would it be okay if we only handle letters? Yes. I think so, as long as that's what the assignment says. But frankly, just makes your life easier to use ASCII. I don't like the green screen doing weird things right now, like artifacting. Does that mean that people with green eyes, like, do they like become transparent with a green screen? Other questions? Stream and take 2, yes. Well, I suppose I will end the stream with the quick. I'm gonna open up that message that I sent you guys and summarize some of the announcements that I did there. So extra credit opportunities. But if you find a bug in that app and you submitted it as an extra credit thing, or you still want to, you can still do it. You just have to go online and go to Canvas and submit a copy of the report that you sent to Sam. From Wikipedia, an application of cycle detection. Determining the cycle length of a pseudo-random number generator is a measure of its strength. That's hardcore. I would say an easier use of cycle detection is you don't want to have loops because it's like a short circuit per se. When you're talking about wiring, you know, you don't want it to feedback. Get the greasy mass so we only see your eyes. That's kind of scary. I do have. What is this? Oh, it's a 23andMe. So this should make me a ghost. Yeah. Like, my arm. It was chopped. It's like, all right. Sorry, bored. Coronavirus. Hashtag coronavirus. Cycle detection may be useful as a way to discover infinite loops in certain types of computer programs. I think that's a more applicable usage for us. Infinite loops, I suppose. Yeah, why not? Anyways, other things. Extra credit opportunities. Tries. There's another extra credit at the end of assignment 11 that's independent. That it will be due at the end of, that would be for a final exam extra credit, and that would be due at the end of the month. There's also the notes that you can submit for extra credit, but there is no curve for the class or test 2. Test 2 grades will come up eventually. So what did 23andMe say? That the dog is my dad. I don't know. It said that I'm half European, half Native American, which they call Native American, but it just means Mexican. So we use Topological in the GCC matrix. I'm just saying it's one usage. There are other usages, but then you have to use that nasty Geeks for Geeks algorithm that is like that takes actually effort to understand. So will there be an assignment 12? Yes, that's the final project. It's just called assignment 12. That's the extras. And yes. Oh, big thing I suppose I should say. The final exam, tentatively on Friday of study week potentially. So I want to hear feedback if that doesn't work with people. Otherwise, I'm going to make a Canvas one question quiz again to confirm with everybody that that's okay. 12-hour time period, just like we did test 2, with some slight modifications. I think the biggest thing that people wanted was one upload with all questions in it. And I think that will make people's lives easier, quote unquote. I think for questions that don't require drawing, we can still make them separate to still make it easier. And then just have all the uploads together for all the non-text questions or questions that require more than just text. Extra credit for assignment 11 is actually quite unrelated to assignment 11, but it's attached to assignment 11. And that is for creating a program. That's a really hard thing, actually. I don't expect anybody to do it, but I wanted to post it anyways. But hey, it's for the final. That's to make a program that will generate graphs so students in future generations can actually use that to look at their graphs and visualize them better. What if you could upload a folder of PDFs? Oh, that just sounds nasty. I mean, in that case, you could just upload them individually. That wouldn't make a difference. How about the negative questions? So I'm not questioning every one of your questions. Well, but see, that's I don't know. Okay. I'll wait and see on the results of the class as a whole before figuring out how negative questions turn out. You can American as a Native American. Yeah, no, not that kind of Native American. I think it's just Native Americans and like the like it just says for anybody who has parentage in Mexico would show up as Native American. Doesn't mean that in fact I don't think I have any like the way you understand Native American as like a Cherokee or something. No, I don't think I have any of that. But yeah, we'll wait on the results of the test. There has been at least one person's test that has been graded, as far as I know. So we'll wait. And then once people gets graded, then I'll do that stream where we can actually see people's grades. Oh, sorry, whoa. That's not what I meant to say. I'm a stream where I do the test for you live, and then you can see it just like how we did in person. You can see whether it was graded right or wrong. Because if I do that now, and then you get your test back like 2 weeks from now or something, which I hope is not that long, then you will have forgotten and you have to rewatch it again. Whereas it's better to have your answers with you, And then that way you can argue if something is right or wrong, and then we can give you the points back. So I think it's better to wait on that stream. One suggestion I have for the next test is to make the nodes letters or numbers. The reason why I made them symbols was so that you didn't just plug and play into your homework assignment. And if you understood how to convert it easily into numbers and letters, which is easy actually, then you probably understand graphs, or sorry, trees in general. So I wasn't worried about that at that point for you. And I'm fine with the follow-up question if they are more like quiz and not giant monsters you made for the exam. They were not too bad. I mean, it's a test, you know. It's like it's only worth like what 20% or 15% of your grade, you know. So have to make it as big as advertised as. I'm almost tempted to leave the final as 1 million points, but then I have to do the math for each question. It would be like 10,000 point question, 100,000 point question. It does take more time, but I was hoping people would just copy and paste the symbols in Paint and then get it done quickly. So yeah. How is topological sort similar to the depth first search? It's more of how they're similar in the sense of implementation wise. If you're implementing it using the algorithm that they talk about, which is depth first search uses a stack. So you use a second stack in the implementation that they're doing. But I don't want to get too deep into that because I have to spend an entire lecture just trying to explain that after I myself have actually understood it. Whereas my method that I showed you is dumb and easy, but works. Maybe not as efficient. I don't know. I think it's efficient, personally. I don't know if it's the best and most efficient, but I like my method. It's easy. That method, you know, would require me to actually understand it. But feel free to check it out. And in a test, you can use it too. I'm not going to make you use my method. Plus the symbols, I try to make them like easy, like hieroglyphics. Like I think the hardest one was like the Death Star or the TIE Fighter, but they were all relatively meant to be simple. Although I do hear people did not like using Paint in the test, so I'll give you that much. Like people cried with Paint. They switched to paper eventually. I would have just done both things, you know, Paint for one question, paper for others. Well, I have the iPad. I love that thing. It's amazing. I hate Apple, but I like the concept of the tablet to draw. When I came up with the test, like I can show you. Hold on a second. I don't know why there's that drawing there, but that's the original. That's the OG picture of that. And I think this is the AVL question. This is my scratch pad of coming up with questions. Sorry, there was a picture I didn't want to show, a drawing that I had that I didn't want to show in a video. Yeah, so I think this is the solution to the AVL tree. There's that picture right there on the top that I used for the test. So then this is all the other stuff, and then this has nothing to do with it. This I was trying to compute some Kerbal Space Program like trajectories for space. So yeah. But yeah, that is so much nicer to do with a tablet. I recommend if you guys can afford it to get a tablet. Don't get the Apple stuff. Just get something cheaper. Get one of those draw pads. I always wanted one for a long time, but I never got around to doing it. Puppy time? Puppy's gone. She's not around here, so sorry. She's chilling. I apologize. Yeah, sometimes she's just literally chilling back here, but not today. I think since my dad is visiting, he took her out to work out, like to walk, and she's tired, probably sleeping. What else? Like I said, at 2:30 p.m. I have the other live stream, so I will end this pretty soon because I do want to take like a break. Grading system. Read the thing on the grading system. Summer tree has not been announced, so don't ask me what's gonna happen with my CS219. I don't know.
Like, I'll do whatever they tell me to do. If it's online, then it'll be just like this system. If it's in person, then it'll be just like in person, like we had class before. It doesn't affect me. Now, I know some of you like can only do it if it's online or not. Unfortunately, they don't tell us these things yet. I don't think they even know themselves. And it's okay, because, I mean, we don't know what's going to happen. Like, you know, especially with the situation going on in the world, we don't know, like, how things will be in a month from now for sure. I mean, we have an idea, but we don't know for sure. So what I did hear, though, the rumor is that even when things start over again in person, that people that are quote unquote high risk, and I don't see that in an offensive way. I'm just saying, like, if you're considered a high risk individual, I think they're trying to make it to make it so that there's an option that you can take things at home, even if we are doing it in person. Which in my case would be just what I'm doing, uploading the lectures, like how I was doing it for the last like 2 weeks or so before we jumped into online only. So that way, people that are not coming into the lectures could still keep track up from home. So yeah. When are we going over the test? We will go over the test in a bonus lecture stream after you get your grades back, so that you can go over it with me. If I go over it now, you see the answers, you forget the answers. Whenever you get your grade back, something is graded right or wrong, you have to rewatch the video. It's a waste of your time. So I'd rather just watch it once, even if you even want to watch it, if you got something marked off, so that you can confirm whether it was graded correctly and justly. And if it's not, then you can let me know. So we'll do that afterwards. Should we take your summer SQL class? Well, let's put it this way. I think MySQL is a very useful thing to know. However, if you're in CS, there is CS 457, I think. I don't know what the name of the class is, which is called Database 1, which I recommend everybody take as their CS elective, which Dr. Taiba teaches, which is really, really good. That's the guy that I'm covering for at 2:30. Not covering, guest lecturing for the support vector machine stuff. And so I recommend you take that class. And if you take that class, you're going to learn MySQL and more, because it's this 400 level CS class. So if you're going to take that class, if that's what you want to take, then I wouldn't take the SQL class in the summer. Because the thing is that SQL class, while it's very useful for you guys, I think, I don't know if it counts as an elective towards your degree, and I don't want you to waste your money on something that is potentially not going to count. And if it doesn't, I'm still going to stream it. You can just come to the stream, and if you're not enrolled in the class, and then you can just take it easy. Of course, assuming if I don't have enough people for the class to run, then I don't know if it's going to get canceled. But assuming it's not, then you can do that. If your degree is not CS, or if you have no intention of taking that database class, then yeah, you could take it. It's a money thing at the end of the day. So I don't care if you guys just sit in by sitting on the stream. You can do that too and learn as much the same way. I just don't want to scam you guys and make you pay for money for something that doesn't count towards your degree. I feel a little bit bad about that. It's mostly for people that are not computer science majors who don't know programming, and I'm going to aim it at that as well. So it might go a little bit slow for someone who could pick up SQL quickly. In Tagba's class, I believe in 3 weeks you're up and running in SQL, maybe even less. Here we're going to spend like 3 weeks, but summer weeks, which is like daily class. So different paces for different people. It's like the Python class, the CS 140 Python class. It's literally 135 in Python. It's even slower than 135. So, you know, I would say somebody of your guys' caliber would be falling asleep in that class because it would be going way too slow. You know what an if statement is. You just need to know the syntax in the Python for that. It takes you 5 seconds to know it, maybe an hour of practice to actually remember the syntax forever. Then you're good. You don't need to spend an entire class lecture understanding the concept of decisions with an if statement. You know that. You learned that already. You've used it for years at this point. You're on the wait list for that class. Which one? The summer class? The SQL class? That is, there's like 6 people enrolled, and there's a lot more spaces than that. You don't need to be on wait list for that. Oh, the database class you probably mean. Yes, as you can see, it's a popular class for a good reason. So he teaches it once a year, I think. 457, yeah. So it's unfortunate. I would stay on the wait list and hope for the best. If not, then there's always a year from now, I suppose. I'm sure that if you're in 302 now, you probably still have maybe a year left or more. So you could take it later on, and hopefully by then you have more credits, and you can enroll. It's unfortunate the situation happening with the classes, especially right now. We were hiring more people, and everything got frozen because of this. And so now we're really tight on the number of classes that can be available. And you guys are basically the people to suffer for that. So sucks, but we're all in this together. All right then. I don't see any more like actual questions on the lecture, so I am going to go ahead and end the stream. I will be available on Discord for a little bit more. Oh, talking about Discord, let's check out the questions that we have. I think the stream just ended. It's offline. Oh, there's way to mic drop. We're back. He's back. Where did we doc say we can see the exam questions? Oh, so if you click, and ask me on Discord this later if you're still stuck. If you click on the test itself now, it should allow you to see the questions now. Maybe somewhere in there you gotta click somewhere, but if you do that, you will see the questions. So if you get stuck, ask me on Discord and I'll forward you to the person that tested that for me, and to see what they did. But I think you just gotta click around in the actual tab. Like if you were gonna take the test, basically, again, you click on it and then somewhere there you see the option. Should be able to see the cameras was graded. Yeah, point breakdown. I think that's what it's called. Mic drop again. Did we die again? I don't know. I can see the internet is flying all over the place. Anyways, I hope it's okay for the 2:30 p.m. class. I'm scared now. All right then. We got 10 people left in here. Next test, I gotta find a better method than paper and pencil. You good? Okay, cool. All right then. Well, that's it. I will see you guys on Thursday, where we will talk about minimum spanning trees. Come to the lecture at 2:30 if you want to learn about support vector machines, or check it out on YouTube later on. Because of that lecture, I'm not going to start uploading this lecture until after the lecture ends. So instead of being available at 6 p.m. as usual, it might be available a little later on at night. But if you're here, you probably saw it. So it's more for the people that weren't here. But I will get it uploaded later. Just the same with the support vector machine lecture before the end of tonight. Yes, it's kind of trippy. All right then. Well, thank you for coming. I hope you guys have a good day. For assignment 11, are we prepared to start it? No, you are 100% prepared for starting it. I recommend that you start it and you code everything but the minimum spanning tree. You can do everything but it about it. In fact, I'll talk more about the assignment on Thursday, but you got to make a graph. You have a lot of choices in that assignment. You can make adjacency list or matrix, whatever you want. Make that graph, get the graph working, and once everything out there is ready, you even at that point worry about minimum spanning tree. Before, you don't have to worry about that. So I will do all of that. That is an assignment of its own. I could have made it, and in the past I have made it an assignment of its own. I decided to combine everything together into one bigger assignment this time, which is why it's worth a lot of points, because it's technically 2 in 1. So I would get started on that first step, and then just leave the minimum spanning tree for the weekend, basically. All right then, I will head out now. Thank you for watching. Thank you for staying. Stay safe, and I hope you guys have a good day.